Een betere wereld begint met het besef dat er nog een wereld te winnen is. Een wereld waarin gelijke kansen de normaalste zaak van de wereld zijn. Zonder voorsprong. Maar wie zijn wij om iets te zeggen als nog geen 30% van onze top vrouw is? Goed bezig zijn is niet goed genoeg. Ja, er is een hele wereld te winnen. En dat begint bij onszelf. Maar daarvoor hebben we mensen nodig die een verschil kunnen maken. Zoals jij. Begin bij ons.
Hello JSpring. Good morning, good evening, or good middle of the night, depending on your current time zone. My name is Aurelio Garcia-ribeyro, and I have been a product manager for the Java platform group at Oracle for a few years now, since before the launch of JDK 7. As much as I wish we could be doing this in person, for this time I'll be joining you from sunny California. I want to thank the Netherlands Java user group and the JSpring conference organizers for letting me share some of what we have recently delivered in JDK 16 and what is currently in the plans for JDK 17. Since we only have 25 minutes, I won't be able to go into much detail, but hopefully I will give you an idea of which features you would like to learn more about. Let's dive right in. It's been almost 3 months since we released JDK 16, and thanks to the 6-month between release cadence that we adopted in 2017, this means that we're exactly 3 months and 12 days away from the next JDK release, which happens to be the second long-term support release under the new release model. Can I still call it new after almost 4 years? Oh well. The number of changes that we have accumulated since JDK 11 is similar to the number of changes that we used to see on the monolithic massive releases of yesteryears. But there are two very important differences. The first one is that we have had time to adapt to these changes in a more regular manner. When JDK 8 released, it took months, in some cases years, for tools and libraries to be ready to use it and support it. Now, since many tools and libraries have been adding support for the new features in 6-month increments, those tools and libraries are able to use and support new JDK versions much faster. The second change is the quality of the features when they are released. The features that were added with JDK 8, for example, were in some cases quite large, and outside of a few heroic testers that tried early access builds, were not real-world tested. We therefore needed a few update releases after GA to stabilize each major release, which in turn slowed down even more the adoption. With the more frequent releases comes the opportunity to test things much more widely before making them permanent. We introduced preview for language and JVM features and Incubator modules for APIs and tools. Although it takes a few additional steps to enable preview features and incubators, having them on GA releases has made it possible for features to be tested in the real world, and in many cases has helped shape those features so that by the time they're finalized, they're real world ready. With every JDK release, we want to have a good mix of features. There are some features that make it easier to write some new programs. For example, language features like lambdas in JDK 8 or records with JDK 16 change how we write new applications. They make code less verbose and easy to read, and sometimes make it possible to have new approaches for certain problems. Likewise, we sometimes introduce new APIs and tools that simplify common or difficult tasks, like accessing memory outside of the Java heap or packaging applications in a way that is more convenient. The benefits of these features are visible immediately to most developers, and hopefully they drive them to want to use the new versions. You won't get those benefits unless you write a new program or update an old one to use them. Then, there are some features that will improve how Java applications compiled on all the JDK versions run. They make it so that your application uses less memory, or runs faster, or works on a new architecture that might not have existed when you wrote your program or library. These are changes to the Java virtual machine and the refactoring of existing libraries. You don't have to write anything new or even recompile your old code to get these improvements. You just run on a newer runtime and automatically get the benefits of these features. These are the changes that make system administrators want to run on a newer version, even if the code itself remains unchanged. As I said before, we also have previews of new features. They're meant to be used only if you're okay with your application not running on future versions of the JDK without you having to update it. Although usually future versions of the JDK will have very similar functionality, and it is likely that it would be very little work to make those things work, there is always some work involved in moving a program that uses previews to the next release. And there is a non-zero chance that a preview might not even make it to permanent. Still, adventuresome users or those who are desperate for the features can try them out. Finally, you can move forward effectively without removing things that hold you back. As hard as we work to add only things that will be useful in the long run, sometimes the industry moves in a different direction, and sometimes things don't work out as planned. In some cases, keeping something around for backward compatibility, even if not widely used, is okay. But in other cases, the cost of keeping things around is too much and impedes further progress. This is arguably the hardest part of being a steward of a platform, making the hard choice of not carrying something forward. Whenever we need to drop a feature or make an incompatible change, we aim to follow a process that will reduce the chance of users being surprised by this. We will mark the feature or tool as deprecated for removal in a release. That has the effect of making the feature by default not work as it did, produces compiles and sometimes runtime warnings. When a feature is deprecated for removal, the feature is still available for use on that release and can be used as before, sometimes simply by handling some extra warnings and sometimes with a command line argument or some other setting. A deprecated feature will remain on a release for the whole lifetime of that release. So for example, we have proposed with JDK 17 to deprecate for removal the Security Manager. This means Security Manager will remain available for all updates of JDK 17. After a prudent number of releases after deprecation, and that number is not fixed but depends on factors like how well adopted is the feature and is there a good alternative readily available, a feature will be dropped from the JDK. So we will also see some removals of previously deprecated features. All JDK versions also include thousands of smaller bug fixes and minor improvements that are called out in the release notes, but that don't warrant a JEP. Finally, we also use JEPs to deliver changes that are only visible to developers of Java. That is, those collaborating in OpenJDK projects. Those changes, like the change of source control software from Mercurial to Git, or moving a port of the JDK from the ports project to the mainline, is not something that users of the Java platform will see directly. Several of the JEPs listed for JDK 16 and 17 fall in this category. Okay, enough with the introduction. Let's see the changes. First, let's look at the language features, since these are the changes that will be most visible to all developers, and they are the most fun to showcase. JDK 16 adds records, which save developers the need to deal with some of the boilerplate one had to create when writing a class that simply aggregates immutable data. Take, for example, a simple class to express a coordinate. We just want to pass around an immutable pair of integers, x and y. But we're going to need a constructor to set those values. And we want all classes to implement an equals. And let's not forget hash code. It would also be useful to see the values from the class if we use toString. And we want to be able to access those values, so we need methods to read them. All of this extra code could be auto-generated by your IDE, so writing it is not a big deal. But that doesn't help us when trying to read the code and understand what this class is for. We'll have to review all of the auto-generated code before we can be sure that this is boilerplate and there is nothing but ceremony behind those methods. What if we could let Java handle all of these for us? Instead of saying class, we say records, and the compiler can make sure that our record types get all of those required methods without us having to include them in our code. If for some reason some of those methods weren't just boilerplate, let's say you need a constructor so you can do some validation in the incoming data, well, you just need to implement the constructor, and the compiler will provide the other ones. This way, whatever is written is indeed required, and when reading the code, you only see things that are necessary, no boilerplate. In some future JDK version, we plan to make it so that you can use pattern matching on records. JDK 16 also delivers pattern matching for instanceof, which allows us to express the conditional extraction of components from objects in a more concise and safe manner. Let's see an example. We've all seen or written code like this, right? We have an object which could hold different types, and we want to do something if it happens to be of a particular type. In this apparently simple statement, we have three things going on. First, we have to test to see if the object is a string. If it is a string, we have to declare a new string variable so that we can cast the object. And we have to cast the object into the new variable so that we can treat it like a string. Using pattern matching, we can reduce the code into a single line that does all of those three things. The variable s is only created if the object is a string. If so, the object is automatically casted into the variable, and the variable is in scope only inside the brackets of the if statement. If there is an else part of the conditional, the new variable is not in scope in the else part. Even with more advanced conditionals, the scope of the variable behaves as you would expect. For example, when using and in a conditional, since the second part of the statement is only evaluated if the first part is true, s is also in scope for the second part of the condition, and in the brackets for that branch. If we were using or, however, the second part of the expression would only be evaluated if the first part is false, so the variable s is not in scope after the or, and can't be used in the second part of the conditional or inside the brackets. JDK 17 adds, as a preview feature, pattern matching for switch expressions and statements. Being a preview means that this change is not yet permanent, and using it will require a command line argument at compile time and at runtime. Pattern matching for switch allows expressions to be tested against patterns, also better seen with an example. Current switch statements work on a few types: numeric, enums, and string. If we wanted to use patterns to check for a certain number of possibilities, we would need to use a chain of if-else statements. Using pattern matching in a switch expression, we can make this more clear. A bonus point is that this code is optimizable. Remember that the case statement has to be exhaustive, so in most cases you want to add a default value. But there's one thing missing here. Traditionally, switch statements and switch expressions throw a null pointer exception if the selected expression evaluates to null. Testing for null is done outside of the switch statement. But now that the case labels will allow for type patterns, it would be better to integrate the null into the switch statement. This makes the code much easier to read and maintain. After a successful pattern match, we often need further tests, which can lead to cumbersome code like this one. We could improve readability if the pattern supported a combination of pattern and Boolean expressions. So, guarded patterns allow us to write these in a clearer way. There are a couple of new gotchas that arise with pattern matching for switch. The first one is that a pattern will dominate later patterns. It is possible to have an expression match multiple labels in a switch block. This is allowed, but they must be placed in the right order. The first example here is very similar to what I just showed for guarded patterns, but with the order reversed. Since the first label will catch all strings, including strings of length 1, the second label is never reached. It is dominated by an earlier case. This will result in a compiler time error. Another new possible error is to have a fall through when declaring a pattern variable. In the second example, if the variable was a character, it would print character, but then, as there is no break statement, execution would flow to the next case label. But since the variable I declared in the second pattern would not have been initialized, we would get an error. It is therefore a compile time error to allow flow through to a case that declares a pattern. Falling through a label that doesn't declare a pattern is fine. JDK 17 adds sealed classes. They are available as a preview in JDK 16. Sealed classes and interfaces restrict which other classes or interfaces may extend or implement them. In Java, a class hierarchy enables the reuse of code via inheritance, but sometimes it can be used to model the various possibilities that exist in a domain, like the kinds of shapes supported by a graphics library. When the class hierarchy is used this way, restricting the set of subclasses can streamline the modeling. What we really need is a superclass to be widely accessible, but not widely extensible. So sealed classes. Let's look at another example. A class is sealed by applying the sealed modifier to its declaration. Then, after any extends and implements, the permits clause, which specifies the classes that are permitted to extend the sealed class. A sealed class imposes 3 constraints on its permitted subclasses. The sealed class and its permitted subclasses must belong to the same module, or if declaring an unnamed module, to the same package. Every permitted subclass must directly extend the sealed class, and every permitted subclass must choose a modifier to describe how it continues the sealing initiated by the superclass. It could be final and allow no more subclassing. It could in turn be sealed, which means it will have its own set of permitted subclasses. In this example, let's make those final. Or it could be non-sealed, a sealed class cannot prevent its permitted subclasses from doing this. One and only one of the modifiers, final, sealed, or non-sealed, must be used by each permitted subclass. Java Lang class will get 2 new methods, so that code using reflection will be able to determine if a class or interface is sealed, and if so, to get a list of the permitted subclasses. Now, while changes to the language make it easier to write new code, changes to the Java virtual machine are often improvements that everyone can take advantage of, even if all you're doing is running code compiling an older version on this new release. The engine that runs your Java program has improved, and as such, you will get better performance on all programs. JDK 16 brings us 2 such changes. For those using the set garbage collection, which is not the default but has been available in experimental mode since 11 and non-experimental since 15, JDK 16 delivers an improvement on how garbage collection is processed. With JDK 16, we moved the last important part of work that was being done in save points to the concurrent phase. This removes the last roadblock for making CGC take advantage of parallel processing and was a requirement for the CGC goal of sub-millisecond types in save points. The second JVM enhancement is on the area of memory management for metaspace. Before this change, when the memory on metaspace was no longer needed, it was returned to the JVM, but the JVM in turn did not return it to the operating system promptly. With this change, the JVM now allocates memory in smaller chunks, reducing class loader overhead and fragmentation, which makes it easier to return the unused space to the operating system. The JDK will now be able to return memory to the operating system more quickly, so applications will now run with a smaller total memory footprint. Changes to the libraries can either provide new functionality or improve existing APIs. With JDK 16 and 17, we bring in a few new APIs. Some of you might make use of these APIs directly. Others might benefit when the libraries you rely on improve by using them. JDK 16 brings us Unix domain sockets, which are similar to TCP/IP sockets, but are meant to be used for inter-process communications rather than for communicating with other servers. They can be addressed by file system path names rather than Internet Protocol ports and numbers. Unix domain sockets are more secure and efficient than using the equivalent TCP/IP loopback connections. Unix domain sockets channels are used by all major Unix platforms and by Windows. This JEP will add support for the features that are common across Unix and Windows. Until a few years ago, the recommended way to use Java on a system was to have a single shared system-wide Java and run all Java programs on it. This meant that Java applications delivered as jars behave differently. You first have to install a Java runtime and then distribute a jar and somehow pass the jar to the runtime. Windows users, for example, won't find an entry for the Java program in the start menu. It won't be listed in the add remove programs list. And more importantly, Java programs cannot be distributed using standard tools for each platform, like RPM packages and Yum repositories from Linux. Using this new packaging tool, you can wrap your application plus a Java runtime, either a full runtime or a smaller version if you use JLink, into something that looks like a native installer for each platform, delivering an MSI installer for Windows, or a DMG for macOS, or an RPM or Debian package for Linux. JDK 17 refactors some of the code used to generate random numbers. We wanted to add the option of generating a stream of pseudo-random generators and allow for more modern algorithms. The prior implementation added unnecessary constraints to uses of PRNGs classes and had very similar, almost copy and paste implementations. Refactoring to a common location makes further maintenance simpler and provides a framework for accommodating future algorithms. With the release of macOS 10.14 in 2018, Apple announced its intention to move away from OpenGL APIs in favor of a new rendering pipeline with better performance called Metal. The Java 2D API used for the macOS port used the OpenGL APIs. Java 2D does have a software rendering option, so it can manage without using the OpenGL APIs, but the performance using platform-specific APIs is much better. Although the default pipeline remains OpenGL, the system will now fall back to Metal if OpenGL fails, as we expect it will if Apple removes support for OpenGL. You can also tell Java to use the new pipeline. If you use macOS, we'd like you to try this and report any issues to the OpenJDK Lanai project mailing list. We hope to be able to switch to the new pipeline by default before Apple stops shipping with OpenGL. Both JDK 16 and 17 offer, in an Incubator module, a vector API that will give developers a way of expressing computations that will reliably translate at runtime to vector hardware instructions on supported CPU architectures. Vector operations enable more work to be performed in a single CPU cycle, so this can lead to significant performance gains. Now, most developers will not have to do this directly. We expect that library developers will take advantage of this API to optimize common libraries that most developers rely on. Once that happens, most developers will experience significant performance improvements merely by updating to a newer version of those libraries and running on a newer JDK version. Here's a conceptual example. If the same operation will be executed on a group of values, it might be possible to load those values into vectors and execute the operations on the complete set. In this example, rather than needing 4 multiplications, 4 additions, and 4 assignments, we can get to the same result with using CMD instructions for 1 multiplication, 1 addition, and 1 assignment. Operations that might benefit from the vector API are common in cases like machine learning and cryptography. We also get to test 2 APIs courtesy of Project Panama that will make it simpler to run non-Java code for now specifically C libraries on x64 and ARM64 platforms. Although Java has supported native method calls using JNI since Java 1.1, this has always been hard and brittle. Using JNI requires developing and maintaining multiple artifacts like a Java API, a C header, and a C implementation. And this must be done for each supported platform, making the effort platform dependent and require different tool chains in each platform. Other frameworks and tools have appeared over the years that improve on JNI, but they're still less than ideal. Project Panama aims at making it trivial for Java developers to use any native library. These APIs provide the foundation for Java programs to interact with native libraries. Now, there was an unfortunate interaction between the Java language and JVM semantics and floating point coprocessor instructions used on the early x86 systems, making it so that Java had to manage a large overhead of instructions to deliver floating point operations. Matching results, in the absence of overflow and underflow, could be done much more efficiently, but that required relaxing the Java floating point semantics, which is what was done with Java 1.2 as an implementation option. Now, around 2001, processors started offering a new set of extensions that would allow the more strict floating point semantics without that additional overhead. So we're now going back to string floating point semantics as the only option. This is unlikely to affect existing applications, as a strict execution was always an option. Moving a platform forward is not only about adding new features. It is also about making sure that programs behave correctly and are not doing anything that will make it harder to uptake future versions. One of these contracts between the maintainers of the Java platform and the developers that use it is that there is a set of APIs that developers are welcome to use and which future versions of the JDK are likely to continue having. In order to deliver those APIs, the maintainers of the platform use internal APIs meant to be used only within the platform. These internal APIs are subject to change without notice, and therefore any program that relies on them might break when applying any update. Until JDK 9, internal APIs were not documented, but since the developer have access to the source code, they're easy to find, and once found, can be called like any other API. Although there are warnings when compiling with those APIs, some developers still rely on them. Even if you're not using them directly, many common tools and frameworks use them. So for many years, most, if not all, non-trivial applications relied on them. With JDK 9 and the introduction of Jigsaw, we have the ability to enforce that only JDK internal code should access those internal APIs. But turning that on by default on JDK 9 would have made it so that all of those libraries and frameworks would have stopped working with little notice. Instead, we choose to only add more explicit warnings for JDK 9, and we said we would wait a prudent amount of time before we started enforcing encapsulation. 3.5 years later, a prudent amount of time has passed, and we are therefore enabling a strong encapsulation by default. With JDK 16, we're going from still accessible but with warnings to no longer accessible by default. It is possible in JDK 16 to relax encapsulation with a single command line option. With JDK 17 and later, the single command line option is gone. So if you insist in using internal APIs, you will have to open specific packages one by one with the add opens command line option. As part of Project Valhalla, we're working on a new type of class for Java called primitive classes that will be used for instances that will be identity-free and capable of inline or flattened representation. Now, some of those classes that currently exist in Java will be converted to primitive classes. Those classes are currently called value-based classes in the API specification. The primitive wrapper classes, such as Java lang integer or Java lang double, satisfy most of the requirements to be designated value-based classes, except that they expose public constructors that have been deprecated since JDK 9. The recommended way of creating these classes is using a factory method. With this JEP, the constructors are not only deprecated, but have now been tagged with for removal equals true. So you will get new warnings if you try to use them. Additionally, the JDK will now emit warnings if you try to synchronize on instances of any value-based class or when accessing. When possible, you will also get compile time warnings. JDK 17 brings two deprecations with for removal. Features deprecated with for removal will work on JDK 17 for the whole lifetime of the release, but will be removed in some later versions of the JDK. The first one is APIs that we use to support applets. They have been deprecated since JDK 9, but were not yet tagged for removal. Adding for removal means additional warnings when compiling code that uses these classes. The second one is the security manager, which has been available since JDK 1, and which was used to create the Java sandbox where untrusted applets were meant to run. Although the security manager, in theory, could have been used to help protect server-side code, in the real world, it was rarely used for this purpose. Furthermore, many of the security risks of modern systems cannot be addressed by the security manager. Of the 25 most dangerous issues identified by industry leaders in 2020, the security manager could only help protect against 6. The details are listed on the JEP if you care to review them. You might think, still, why not keep it around to protect against those 6 concerns? But to use it as intended requires developers to adopt a permission model that is quite brittle and difficult to maintain and has serious performance penalties. All of this has resulted in very low adoption for security applications. The cost of maintaining the security manager is quite high, as it must be tightly woven into all Java class libraries, which imposes an unacceptable tax on future developments of the platform. Although it has not been widely adopted for security, there are other use cases for which the security manager has been adopted. Some frameworks use it to keep managed code from calling system exit or to gain insights into whether an application opens connections to ports or files. These use cases can be addressed by much cheaper alternatives. One of the goals of deprecating the security manager is to help us identify other use cases we might have missed so that we can find or add alternatives before it is removed from the platform. It is too early to tell when these features will be removed from the platform. As with prior deprecations, we will consider feedback to decide when most users have had enough warning and have switched to alternatives. As implied by the previous slide, things that have been deprecated for removal eventually are no longer included in later versions. JDK 17 no longer includes RMI activation, which was deprecated for removal since JDK 15. The rest of RMI remains unaffected. The other removal is not a feature that was included in the platform, but an experimental set of features that was considered for inclusion around the release of JDK 9. The experimental ahead-of-time compiler and just-in-time compiler have seen very little adoption, and the cost of maintaining them is not small. These features being optional, they were already excluded from Oracle's build of JDK 16. Finally, not all of the work in the JDK releases shows up directly in the binaries. JEPs are also used to deliver improvements to the OpenJDK project. Here's the list of changes in OpenJDK. For example, the first one about enabling C++14 language features is not about adding those to Java, but allowing those features in the C++ portions of Hotspot. The ports listed do not imply that Oracle or other vendors that build from OpenJDK must offer builds of those ports. These JEPs just add the source code for those ports to the JDK mainline. If you want to learn more about any of these features, you can go directly to the source of truth and visit openjdk.java.net. Each of these JEPs has a detailed description, from which most of the text in this presentation was borrowed, but offers a lot more detail. The JEPs also point to the relevant discussion list, which has even more details not only on the feature, but also on the discussions that led to it. If you would like to weigh in, especially about preview features and API and tools in incubators, that is a great place to start. Oracle customers, developers, and those looking for a Java runtime for personal use can download JDK 16 from the Oracle Java download page. Those interested in OpenJDK work or those that want to preview JDK 16 early access builds should visit jdk.java.net. JDK 17 will come out on September 14 and will be available in the same places. For more information about Java SE, visit our Java homepage, follow us on Twitter, or contact us via email. If you'd like some insight into some of the deliberations that go into choosing which features to add into the JDK, you should attend my colleague Nikolai Pavlov's session later today. Thank you and enjoy the sessions.
Een betere wereld begint met het besef dat er nog een wereld te winnen is. Een wereld waarin gelijke kansen de normaalste zaak van de wereld zijn. Zonder voorsprong. Waarin de innovatie van vandaag niet de zorg van morgen is. Een wereld die geen filter nodig heeft om schoon te zijn. En waarin geld schoon is zonder het wit te wassen. Maar wie zijn wij om iets te zeggen? Nog geen 30% van onze top is vrouw. Slechts 15% van onze hypotheken is duurzaam. Tikkie blijft niet eeuwig nieuw. En we hebben witwassen nog steeds niet de wereld uitgeholpen. Goed bezig zijn is niet goed genoeg. Ja, er is een wereld te winnen. En dat begint bij onszelf. Maar daarvoor hebben we mensen nodig die een verschil kunnen maken. Zoals jij. Begin bij ons.